In the last couple lessons, we've talked quite a bit about solving systems of linear equations, spending most of our time on systems with two linear equations and two unknowns or variables. In this lesson, I'd like us to push further with this idea by considering systems of linear equations with three unknowns. So we'll have three equations and three variables. We definitely don't want to solve these kinds of systems by graphing. I've talked about that in a previous lesson. But we can certainly use the method of elimination in a smart way to find the solution of a system with three linear equations. So in this lesson, I want to talk through as many examples as we can. So let's get right to it with the following example. I want us to solve this system of three linear equations. 2x plus 3y minus z equals 15. X minus 3y plus 3z equals negative 4, and 4x minus 3y minus z equals 19. Now, your first reaction might be, wait a minute, that's really overwhelming. But don't worry, we really can solve this system, and it won't take anything tricky or magical. What we want to do is choose pairs of equations from the original system which can be combined to eliminate one of the variables. And once we have eliminated one of those variables twice, we'll be left with a system of two equations with two unknowns. And you know how to solve that. We've talked about that in the previous two lessons. So we'll solve that system, and then we'll basically be done. Not exactly, but we'll just about be done at that point. So let's get started in this example by choosing pairs of equations from the original set. First, I want us to focus our attention on the first and second equations. So let me remind you, those are 2x plus 3y minus z equals 15, and x minus 3y plus 3z equals negative 4. Now, watch what happens when you add those two equations together. You're going to get 3x plus 0y plus 2z equals 11. The important thing that just happened is that the variable y was eliminated, and that's exactly what I wanted to have happen. Now, I want to go back to the original set of equations and combine a different pair of those equations with the goal of eliminating the variable y again. I'm going to suggest that we pick the first and the third equations. So here's what I want to do. Why don't you try taking those two equations, 2x plus 3y minus z equals 15, and 4x minus 3y minus z equals 19, and try to eliminate the variable y. Okay, that wasn't too hard, was it? Let's check to see what you got to make sure that you eliminated that y correctly. You should have had, when you added, 6x minus 2z equals 34. So notice what we now have. We now have two new equations which we built from the original set, both of which are missing the variable y. And they are 3x plus 2z equals 11 and 6x minus 2z equals 34. So we have whittled down, so to speak, the original system into a smaller system of just two equations that only has two unknowns. And the important thing is that it's the same two variables, so the same two unknowns in both of those equations. In this case, it's x and z. And now if we add those two equations, we will eliminate another variable. We'll eliminate the z. Adding those two equations gives us 9x equals 45. And now I can find x. I divide both sides by 9, and I get x equals 5. Now, we know the value of x in the solution. It's x equals 5. We should hold on to that because we don't want to lose that. X equals 5 is part of our final answer. Great. But what do we do now to find the y and the z? Well, the first thing we do is we put the x equals 5 back into either 3x plus 2z equals 11 or the 6x minus 2z equals 34. When we do that, what are we trying to do? We're going to try to find z at that point. And remember, you can put the x equals 5 back into either of those two equations. So I want you to try that now. Plug 5 in for x into either 3x plus 2z equals 11 or 6x minus 2z equals 34 and find z. Okay, I'm going to try plugging the 5 in for x into the first equation to see what I get for z. 3x plus 2z equals 11 becomes 3 times 5 plus 2z equals 11 because x is 5. And that's 15 plus 2z equals 11. Subtracting 15 from both sides gives me 2z equals negative 4. And dividing both sides by 2 gives me z equals negative 2. So now I have a second piece of the puzzle. I now know that x equals 5. I knew that a moment ago. Now I know that z equals negative 2. Am I done? No, I still need to find y, but I'm now 2/3 of the way there. I know x and I know z. What do I do to find the y? Well, I go back to any of the 3 original equations that we started with in this example, and I plug in x equals 5 and z equals negative 2 to find y. Sometimes this idea of plugging these numbers back in one at a time to find some of the other variables is called back substitution. So you might see this phrase back substitution in some textbooks as you're trying to find one variable at a time by plugging in the numbers. So let me suggest that you try going back to, let's say, the first equation in the original set of equations to find the y. Plug in x equals 5 and z equals negative 2 into the equation. 2x plus 3y minus z equals 15. And I want you to solve for y. Now, did you get all of those pluses and minuses right? There's a lot of arithmetic here, so let's do this together just to make sure everything worked out correctly. We started with 2x plus 3y minus z equals 15. We're plugging in 5 for x and negative 2 for z, and that gives me 2 times 5 plus 3y minus a negative 2 equals 15. Or 10 plus 3y plus 2, negative times negative 2 is positive 2, equals 15. So I have 10 plus 3y plus 2 equals 15. Adding the 10 and the 2 gives me 3y plus 12 equals 15, or 3y equals 3. And if I now divide both sides by 3, I'll have y equals 1. And guess what? A little at a time, one step at a time, we've just cranked out the solution of this system. It's x equals 5, y equals 1, and z equals negative 2. Now, by the way, did you notice that in this example, I actually found the value of x first, then I found z, and then I came back and found the value of y. The order in which we find the numbers that fit those variables does not matter. You don't have to find the x first, and then the y, and then the z. You can find them in any order. Whatever order is best is the order in which you should try to find those values. Now, before we move to the next example, let's just check to make sure this is really the solution. Let's be honest, there was a lot of arithmetic in what we just did for this one example. So I'm going to suggest we go back to the original 3 equations, plug in the value for x, the value for y, and the value for z, and make sure we really got a solution. So let's do that here. We had, first of all, 2x plus 3y minus z equals 15. Plugging in x equals 5, y equals 1, and z equals negative 2 gives me 2 times 5 plus 3 times 1 minus negative 2 equals 15. And the left-hand side then is 10 plus 3 plus 2, which is 15. So 15 equals 15 is true. That equation is fine. Let's try the second one. X minus 3y plus 3z equals negative 4. Plugging in my information for the solution gives me 5 minus 3 times 1 plus 3 times negative 2 equals negative 4. Or 5 minus 3 minus 6 equals negative 4. And now if I walk through those subtractions from left to right, according to my order of operations, that's going to be the same as 2 minus 6, which is the same as negative 4, and that equals negative 4. So the second equation also checks out. That's good. Let's try the third. 4x minus 3y minus z equals 19. Plugging in x equals 5, y equals 1, and z equals negative 2 gives me 4 times 5 minus 3 times 1 minus a negative 2 on the left-hand side, which is 20 minus 3 plus 2, which is 17 plus 2, which is 19. And that equals 19, which was the right-hand side. And so all three equations were true once I plugged in that information. And that tells me that I had the correct solution, which is fabulous. Now, I'd like to move to a second example, and I'd like to suggest that you try this one yourself. Now, it's going to take some time, and you're going to want to be careful as you deal with all these plus and minus signs, for example. But start the video again whenever you think you have the answers. Here's the system. Let's solve 8x plus 2y minus 4z equals 0, 2x minus 3y plus 3z equals 9, and negative 6x minus 2y plus z equals 0. Well, do you think you got the right answers? Let's check. We need to pick a variable which we can eliminate using two different pairs of equations from the original system of three equations. It doesn't matter which pairs you choose, and it doesn't matter which variable you choose to eliminate first. I'm going to start by picking the first and the third equations in the system, and those were 8x plus 2y minus 4z equals 0 and negative 6x minus 2y plus z equals 0. Now, as with the systems of two equations, I'm allowed to multiply any of my equations by a constant. So I'm going to start by multiplying the equation negative 6x minus 2y plus z equals 0 by 4. And when I do that, I'm going to have the following new pair of equations. 8x plus 2y minus 4z equals 0, which I didn't do anything to, and negative 24x minus 8y plus 4z equals 0. And remember, when you multiply that 0 on the right by a 4, you get 0 back. 4 times 0 is 0. Sometimes students want to write down a 4 there, as if they were doing 4 times 1 instead of 4 times 0. But keep in mind, 4 times 0 equals 0. Now if we add these two new equations that we've built, we will eliminate the variable z. And that's what I was trying to do, was eliminate z. And when I do that, and I make that addition work, I get negative 16x minus 6y equals 0. Now, let's go back to the original system again and see if we can pick another pair of equations with the goal of eliminating z. Since I eliminated z just a moment ago, I need to eliminate z again. It's one of the most important things here, eliminating the same variable twice. This time I'm going to pick the second and the third of the original equations, and I'm going to multiply that third equation by a negative 3. And my new system then, or new subsystem as some people might call it, would be this. 2x minus 3y plus 3z equals 9, and 18x plus 6y minus 3z equals 0. Notice that if I add these two equations together, z will be eliminated again. That was my goal. And when I do that addition, I get 20x plus 3y equals 9. So now I have two new equations that only have two variables in them. Negative 16x minus 6y equals 0, and 20x plus 3y equals 9. Now what do I do? Well, I've just got a system of two equations with two unknowns. We can eliminate another variable now and see if we can come up with the start to finding the numbers in the solution. I'm going to suggest that we eliminate the variable y here if we just play with the equations just a bit. One way to do that is to multiply the second of these new equations by a 2. And when I do that, that's going to give me the following little system or subsystem. negative 16x minus 6y equals 0, and 40x plus 6y equals 18. Do you see why I multiplied by that? Because now the variable y can be eliminated by just adding those two equations. And when I do that, I'm going to have 24x equals 18. I've eliminated the z, and then I eliminated y step by step, and now I'm just down to x. And if I divide both sides of 24x equals 18 by the number 24, I will isolate the x, get it by itself, and x will equal 18 divided by 24, and after I reduce that a bit, that's the same as 3 over 4, or 3/4. So I now know part of my solution. X equals 3/4. And now what I want to do is back substitute to find the y, the value for y. I can do that by using either of the two equations that had just two unknowns in them that I was just working with a moment ago. I'm going to use the second of those, even though it really doesn't matter which of the two I use. I'm just going to pick the second one of those and plug in x equals 3/4 and see what I get. That equation was 40x plus 6y equals 18. And now I know x is 3/4, so I'm allowed to plug 3/4 in for x. And when I do, I'm going to have 40 times 3/4 plus 6y equals 18. Now 40 times 3/4 could be a little tricky, but that's going to simplify to just 10 times 3, which is 30. So I have 30 plus 6y equals 18. Subtracting that 30 from both sides gives me 6y equals negative 12. 18 minus 30 is negative 12. And dividing both sides by 6 gives me y equals negative 2. So now I have both the value for x and the value for y. I just need the value for z. What do? Well, I go back to one of the original equations that we started the example with. I plug in the value for x, and I plug in the value for y, and all that will be left is solving for z. So let's go back to those original equations. I can pick any of the three that I want. I'm just going to pick 8x plus 2y minus 4z equals 0. Now I'm going to plug in 3/4 for x and negative 2 for y, and then I'm going to solve for z. Let's see what we get. We have 8 times 3/4 plus 2 times negative 2 minus 4z equals 0. 8 times 3/4 is the same as 24 over 4, which is 6. So I'm going to have 6 minus 4 minus 4z equals 0. And 6 minus 4 is just 2. So I have 2 minus 4z equals 0. Now I subtract a 2 from both sides, and that gives me negative 4z equals negative 2. And now if I just divide both sides by negative 4, I will have z equals negative 2 divided by negative 4. The negatives will cancel one another. I'll just have 2 over 4, which is the same as 1/2. So if we haven't done anything wrong in all of this arithmetic we've done, then our solution is x equals 3/4, y equals negative 2, and z equals 1/2. And if you got those answers, congratulations. Now, I'm not going to take the time to check that answer here. I'm going to let you do that on your own. Just plug those values into the original equations to make sure that the equations are true. That's going to be our confirmation that we did everything correctly. But let me say a couple things before we move to the next example. First of all, checking that those numbers really work as a solution is important. So just because we're not doing it together right now doesn't mean I think it's not important. It really is important. So please make sure you do it. And secondly, notice that these problems aren't hard, but they are time consuming. They do take some work. They take a lot of care with your arithmetic. You're going to want to be careful about it and give yourself time. Don't get impatient with them. Just work through them step by step and you'll be fine. Okay, let's look at another angle on these systems now by looking at the following example. Here it is. X plus 2y plus 3z equals 10. Negative 2x plus 3y minus 5z equals 30. And 5x plus 10y plus 15z equals 20. Now, how do we start? Well, we start by eliminating one of the variables. We have to sort of eliminate it twice, if you will. We can choose any of the variables to eliminate, but there's really an obvious choice, so to speak. I'm going to suggest that the best one to eliminate would be the x, and that's because the x term in the first equation only has a 1 in front of it. And that basically allows me to multiply that equation by whatever I need so that the elimination will go quickly. So let me show you what I mean. Start by choosing the first two equations, x plus 2y plus 3z equals 10, and negative 2x plus 3y minus 5z equals 30. What would you multiply that first equation by in order to eliminate the x? You're going to multiply it by 2, and then you're going to add. And when you do that, multiplying the whole first equation by 2, remember you have to multiply everything on the left and everything on the right of that equation by the number 2. When you do that, and then you add, the 2x minus 2x will become 0x, and the x will be eliminated, and you'll be left with 7y plus z equals 50. So we've successfully eliminated the x in this one case, and now I have to go back to the original system of equations and pick a new pair that will allow me to eliminate x. Again, you don't want to go eliminating y or z now. You've started down the path of eliminating x. Now you have to do that again. So let's take the first equation. I like it because it has that 1 in front of the x. And the third equation. And that's going to be x plus 2y plus 3z equals 10. And 5x plus 10y plus 15z equals 20. Here's a question. What would you multiply that first equation by to start the process of eliminating the x? Well, you got a couple choices. You could multiply by positive 5 and then subtract, or you could multiply by negative 5 and then add. They're basically the same thing, but I'm going to choose to multiply by the negative 5 and then add the two equations. Now, when you multiply that first equation by negative 5, you must make sure that every term in that equation on both the left-hand side and the right-hand side is multiplied by a negative 5. That's going to give you the following. Negative 5x minus 10y minus 15z equals negative 50. And the third equation, which I haven't done anything with, is 5x plus 10y plus 15z equals 20. So that's my new subsystem, if you will. I want to look at just those two equations. Now, my goal was to eliminate the x. Okay, let's see what we get. We add and we get 0x plus, 0y. The y's have also canceled. Well, that's not so bad, but it wasn't my goal, but that's all right. I have 0x plus 0y plus 0z. Actually, everything on the left-hand side has canceled out. And on the right-hand side, I have negative 30. So we haven't done anything wrong, I promise, but now we're down to the equation 0 equals negative 30. Now, it wasn't wrong that we eliminated more than one variable. That's not the problem. But it is wrong that 0 equals negative 30. 0 is never equal to negative 30. And so that's a problem. Is it our problem? No. We just have to interpret what's going on correctly. What does it mean when we come down to something like 0 equals negative 30? Our first response should be that the original system of equations has no solution. And honestly, that's the answer. There's nothing fancier than that. All we have to know is that there simply isn't a solution to the original system, and that's that. Now, let me ask you, we saw systems in previous lessons that didn't have a solution. Do you remember what they're called? They're actually called inconsistent. So the point of this example is that the system I started us with was actually inconsistent. It didn't have any solutions at all. Now, I'd like to close our lesson by looking at one more example of a system with 3 equations where some of the variables are already missing as you get started. And I just want to make sure we work through this because for some students this can throw them off when they don't see all three variables in all three equations. So let's solve this system. The system's going to be x plus 2y equals 5, x minus 3z equals 7, and y plus z equals 4. Now, you might look at that system and say that it looks really different from the earlier systems we've done in this lesson. But if it really does look different, may I make a suggestion? Why don't you rewrite the system this way? X plus 2y plus 0z equals 5, and x plus 0y minus 3z equals 7, and 0x plus y plus z equals 4. If you insert those extra terms with coefficients of 0, it actually makes the system look a little more familiar. But if you don't mind, you don't need those terms. So I'm going to go back to the way the system looked originally. If you want to keep those terms in, go ahead. It won't hurt. But I'm going to go back to the shorter versions where I don't need those extra terms. Now, one of the beauties of having a system where some of the variables are already missing is that the elimination process is already partly done for us. So we have lots of choices for what variable we want to eliminate in the beginning. So, for example, let's just subtract the first and the second equations to eliminate the x. If you start with x plus 2y equals 5 and x minus 3z equals 7, the first equation minus the second equation is going to give us 2y plus 3z equals negative 2. Now, notice that this equation has a y and it has a z, but it has no x in it. So it's like we've eliminated the x. But notice also that the third equation from the original system, which was y plus z equals 4, was already missing the x. So guess what? We already now have two little equations, both of which are missing x. They only have two unknowns. And they are 2y plus 3z equals negative 2 and y plus z equals 4. So we're already going right down the path that we want to go down. We've already eliminated one of the variables. Now, let's multiply the second of these smaller equations by negative 2. And that will give me 2y plus 3z equals negative 2 and negative 2y minus 2z equals negative 8. Remember, you've got to distribute that minus sign all the way through all the terms. And now if you add those two equations, you just get 1z, or z, equals negative 10. Guess what? We just found z. It's negative 10. Hold on to that. Don't lose that negative 10. And now let's start back substituting to find either the x or the y. In this case, it's going to be easy to find the y first, because we already had an equation like y plus z equals 4, and we know that z is negative 10. So if I plug in negative 10 for z, I'll have y plus negative 10 equals 4, or y minus 10 equals 4, and adding 10 to both sides of that gives me y equals 14. Now you know z and you know y. And if you use those two pieces of information in one of the original equations, you can actually find x. For example, one of the original equations was x plus 2y equals 5. So plug in 14 for y, which you know, and you'll have x plus 2 times 14 equals 5. Now let me pause just for a second. Someone is saying, hey, wait a minute, you didn't use the value of z there at all. But I don't need to. There's no z in the original equation, so we really are fine. And if we start to simplify, we'll have x plus 28 equals 5, which means x equals negative 23. So guess what? Our solution is done. X is negative 23, y is 14, and z equals negative 10. And that's the final answer. Again, you can plug that information into the original set of equations if you'd like to make sure you've done it right. But ultimately, we've actually finished that problem by finding those three values. Now, I'd like to finish today by sharing some thoughts about precalculus, in fact. It turns out that these systems of three equations with three unknowns can be solved by a totally separate method using what are known as 3x3 matrices. A 3x3 matrix is simply a table or an array with 3 rows and 3 columns of numbers. And these matrix techniques, which are often demonstrated in something like a pre-calculus class, can be extremely useful in solving these kinds of systems. In fact, matrices can be used to solve any system of linear equations, no matter how many equations there are and no matter how many unknowns there are. You could literally have 20 equations with 20 variables and solve such a system with matrices. So if you've enjoyed this lesson on systems of 3 linear equations, you'll probably really enjoy studying this topic with matrices. As a small bit of advertising, let me tell you that the teaching company has developed a pre-calculus course, and I know that matrices are discussed there. Next time, I'd like to return to systems involving only 2 variables or unknowns, but this time we'll look at systems of inequalities instead of equations, things with less than and greater than symbols, to see how these problems are different from what we've been studying for the last few lessons.